All right, 5.5, part 4. We're looking at Descartes' rule of signs. Let f of x define a polynomial function with real coefficients and a non-zero constant term with terms in descending powers of x. Okay, so we've got a polynomial in standard form, and then your constant term at the end can't be 0. Okay, then A, the number of positive real zeros, so the number of positive real zeros, so not complex, just real zeros, is either equal to the number of sign changes of f of x or is less than the number of sign changes by an even integer. Okay, so like if you got 6, then it's either 6, 4, 2, or 0. And then the number of negative real zeros is either equal to the number of sign changes of f of negative x or is less than the number of sign changes by an even integer. All right, so this rule allows us to look at just sign changes in a polynomial, which I'll explain in a second, to determine the number of positive real zeros, the potential number of positive real zeros, and the potential number of negative real zeros. All right, so it says to use Descartes' rule of signs to determine the different possibilities for the numbers of positive, negative, and non-real complex zeros of the polynomial. So first thing you need to do is count the number of sign changes in the polynomial, and here's what I mean by that. So we start out with a negative here, and then as I move from one term to the next, the sign changes from positive to negative. So that's one sign change, and then we go from positive to negative here, so that's 2, negative to positive 3, positive to negative 4. So there are 4 sign changes. Okay, so 4 sign changes. So what does that mean? So looking at A, the number of positive real zeros is either equal to the number of sign changes of f of x. So since there's 4 sign changes, that means that there are potentially 4 positive real zeros, and then it says or is less than the number of sign changes by an even integer. So 4, skip the odd integers, so 4, 2, or 0 positive real zeros. And that's how that works. There could be 4 real zeros, 2 real zeros, positive real zeros, or 0 positive real zeros. Now let's do f of negative x. We have to find that first in order to do part B. So we're plugging in negative x for x. Okay, let's simplify that. So we know that when there's an even exponent, the negative's going to go away because negative 1 to the power of 4, just check it in your calculator, is 1. So that negative right here in front of the x is going to go away. So negative 2x to the 4. But this one, since I'll have negative 1 cubed, that negative will not go away. So it gets multiplied by the 3. So it becomes negative 3x cubed. So moral of the story, if you have an even exponent, the sign is going to change, is not going to change. If you have an odd exponent, the sign is going to change. So here, even exponent is going to cancel out that negative there in front of the x. So it's going to stay negative 5x squared. This one, there is no exponent, so just 4 times negative x is negative 4x. Okay, now let's count the sign changes. So we go from negative to negative to negative to negative to negative. There are no sign changes. So that means there are either 0 negative real zeros. Well, I can't go less than 0, so there's just 0 negative real zeros. Let's think about the potential complex, non-real complex zeros. So basically, I have a potential of having 4 positive real zeros, which would leave me with 0 non-real complex zeros. I could have 2 positive real zeros, which would leave me with 2 non-real zeros. And then I could have 0 positive real zeros, which would leave me with 4 non-real complex zeros. Okay, so basically just taking the potential number of zeros that you have for positive and negative real zeros and subtracting them from, well, we know that there's supposed to be 4 zeros total, and so just subtracting that from 4. So I could have 4 real zeros, which leaves me with no non-real zeros. 2 real zeros leaves me with 2 non-real zeros, and so on. So those are our possibilities. For each case. All right, let's do another one. All right, so we'll start by counting our sign changes on number 19. Positive to positive, positive to positive, positive to negative. So we only have one sign change for f of x, which means we must have just one positive real zero. We can't go down any and have just 0 positive real zeros because it says or is less than the number of sign changes by an even integer. So we'd have to go down by 2, and we can't. Okay, so just one positive real zero. So now let's do f of negative x. So plugging in negative x in for all of our x's. And simplifying that. So remember, anytime there's an odd exponent, that negative is going to stay, so negative x cubed. Even exponents cancel out negatives. Negative 1 squared is just 1, so that goes away. That becomes just 2x squared. Okay, so count the sign changes. 1, 2, that's it. 2 sign changes, which means we could have 2, or go down by 2, 0. So 2 or 0, negative. Real zeros. All right, and then we'll see what's left for our non-real zeros. Okay, so I need to have 3 zeros total. Whoops. 3 zeros total because my degree on my polynomial is 3. And so let's think of our possibilities here. I could have 1 positive real 0 and 0 negative real zeros. That leaves me with 2 zeros left over. So 2 of them would have to be complex. Or I could have 1 positive and 2 negatives, and that would leave me with 0. Non-real zeros. If 1's positive and 2 are negative, then I don't have any more zeros, and so I just have 2 or 0 there. So you're just kind of seeing what would be left over for the non-real zeros. All right, let's do one more. So count your sign changes, positive to negative, negative to positive, and that's it. So 2 sign changes on f of x gives us 2, or go down by 2, 0, positive, real zeros. Okay, and then we'll do f of negative x. So plug in negative x for x. Now if you get you can actually just skip writing it down like that and just know that if it has an odd exponent, that is where the sign is going to change. So like this, because the exponent here is 5, the sign is going to change. Because the exponent is 4 here, the sign is not going to change. Right here, exponent is odd, sign changes. Even, sign does not change. Sign changes, sign does not change. All right, and now we count our sign changes. So negative to positive, positive to negative, negative to positive. So 3 sign changes. And that tells us we could have 3, go down by 2, 1, and we can't go down by 2 anymore, can't have negative 1 zeros, so 3 or 1 negative. Real zeros. And now we'll see how many are left for our non-real. Complex zeros. So we could have 0 and 1, so 0 positive, 1 negative, and that would leave us with 4 non-real complex, right? Because we need to have 5 total. Or we could have 2 and 1, that's 3. So I would be left with 2 non-real zeros. Or I could have 2 and 3, leaving me with 0 non-real zeros. And that's it. So we'd have 2 or 0 positive real zeros, 3 or 1 negative, and then 4, 2, or 0 non-real complex. And that's it for 5.5.